Greetings and welcome to part 2 of our Properties of Radicals lesson, Algebra 1.09.01, Big Ideas Math. So in order to do these things, you're going to need to be familiar with your perfect squares, perfect cubes, being able to break up numbers, factor them, so to speak, be able to break these things down. But, before I talk about this other thing, let's take a look at example 5 and talk about our current strategies for dealing with this and why they don't work. And so, first of all, we don't like radicals being in the denominator. That's just the rule, right? And so you might be like, oh, well, maybe I could get rid of that square root of 3 by multiplying by the square root of 3 over the square root of 3. However, what would happen is I'd have 7 rad 3 up top, and then I have to distribute this to both of those terms. So I'd have 2 rad 3 minus, and then rad 3 times rad 3 is 3. And so I got rid of the radical in the denominator, but I introduced another one. And so my normal strategy will not work. So that's weird. There's a trick. Now, because these are perfect squares, it'd be great if I could get rid of them by squaring them somehow. And it turns out it's going to be related to an old pattern that we used to know and still do, sum and difference pattern. A plus b times a minus b is always equal to a squared minus b squared. And what's helpful about this pattern is notice that this term is squared and this term is squared, and there's no other terms. And so if I have square roots that I'm trying to get rid of, squaring each of those individually would be great. And the way I do that is I have to multiply by something, and it's not going to be multiplying by 2 minus the square root of 3. I have to multiply by what we call the conjugate. And so conjugates are not quite the same. They're not quite the opposite, because an opposite would have had a negative a here as well. They're conjugates, where just the middle signs are different, right? It's the sum and difference pattern. And so that's what this is saying here. The binomials, a rad b plus c rad d, and a rad b minus c rad d, are called conjugates. And so notice they're of the form a plus b and a minus b, except those terms have a bunch of other parts involved. And you can use conjugates to simplify expressions that have square roots with a sum or difference in the denominator. And so in order to deal with this, I'm going to multiply the denominator by 2 plus rad 3, and in order to make sure that I'm not changing the value of this expression, I have to multiply the top as well, because that's the equivalent of multiplying by 1, which doesn't change something. And I know that anything divided by itself is 1. So one of the things to be aware of is that this fraction bar behaves as a grouping symbol. And so, yes, this is technically behaving as though it's in parentheses. 7 times 2 is 14. 7 times rad 3 is 7 rad 3 over, now notice this, 2 minus rad 3 times 2 plus rad 3. Sum and difference pattern, it's just going to be a squared minus b squared. Okay, and so you could, if you want, you could try to double distribute, FOIL that out, but let's just use the pattern, save ourselves some work. Here, just a second. Quiet, buddy. Okay, daddy's working. I got the kids hanging out at the house today. I guess I'll let them live here, right? So let's see. 7 plus rad 3. Now in the bottom, I've got 2 squared is 4 minus rad 3 squared is 3. And hey, I can simplify that. That's just 1. And so my final answer is 14 plus 7 rad 3. And I'm done. And notice there's no more radical in the denominator. So that accomplished the thing that I'm trying to do. So just to speed run this concept, what would I have to multiply by here? 1 minus rad 3. And I'd have to multiply the top as well. What would I multiply by here? Rad 5 plus 2 and I'd multiply the top by that as well. What would I multiply by here? Rad2 minus Rad7. Tell you what, I'll actually do that one out proper. So remember, these behave as grouping symbols, so don't forget to do some distributing. 12 Rad2 minus 12 Rad7 all over Rad2 squared minus Rad7 squared, right? A squared minus B squared. So hey, that pattern is coming back to help us. Isn't that wonderful? So let's see. The denominator would be 2 minus 7. The denominator is negative 5. And let's actually talk about how do I address... Let's see. I didn't feel like writing this all down over and over and over again. I'm probably not saving that much time, am I, here? No, definitely not. That's funny. So now the 12s and the 5 do not simplify, but tell you what, let's actually deal with this minus sign. I want to get the negative out of the denominator, and so I'll opposite this term and opposite that term. And so I'll have negative 12 Rad2 plus 12 Rad7 all over 5. And so there's my final answer. So it's still not the prettiest, but it does get the radical out of the denominator. Have you ever looked out at the ocean and wondered how far you can see? Well, this is how it works. At least on our planet, you can see the horizon from your eye level 8 feet above the water, this particular distance. And so the square root of 3h, where h is your height, which in this case is 5 for this individual, divided by 2. And so this is the same as the square root of 15 over the square root of 2. And look, I don't even need a conjugate for this one. No, don't need it. Just Rad2 over Rad2. And so I'd get square root of 30 over 2. But that probably doesn't help this individual because they're like, well, how far is that? And square root of 30, enter, then divide by 2. I'm getting, okay, I was like, this is kind of short. 2.74 miles. Aha. And so there you go. Now you can actually estimate that. That's actually much less than I thought it was going to be. It's interesting. For some reason in my brain, I always had the concept of like, oh, you could see 15 miles to the horizon. But I guess it's not. And so now if you're playing Sea of Thieves, I wonder if the same thing applies. Or question, does Sea of Thieves operate on a flat world? Ooh, peculiar. But I was going to say, Sea of Thieves, you could just hide beyond the horizon sort of thing. So here, question 7. Now here's this concept called a golden rectangle related to the golden ratio. Supposedly it's related to all sorts of beauty and aesthetics and nature, and it's a number. And so it says here are the dimensions if I have that ratio playing. It says the ratio of the length to width of a golden rectangle is such and such. The dimensions of the faiths of the Parthenon in Greece forms a golden rectangle. What is the height of the Parthenon? And so if I have the ratio 1 plus rad 5 over 2, that's the golden ratio, this proportion should be equal to 31 over h. This number, by the way, is bigger than that one. So yeah, the 31 over h. The height is less than the width here. And so let's solve for h. A few different ways you can handle this. Let's cross multiply and just remember that the fraction bar is a grouping symbol. And so I'll have, we'll tell you what, there's a few different ways, but let's say I didn't distribute. And then 2 times 31 is 60 dose. And if I want to solve for h, I could divide both sides by 1 plus rad 5. And so h is exactly equal to this. And then, oh no, I've got a radical in the denominator. And so what do? Well, I can't multiply by rad 5 over rad 5. That won't work. But I can multiply by the conjugate. And so 1 minus rad 5 over itself. And so this 62, I'm going to distribute, because remember, that's grouping. Remember, oh dear, did I give myself enough room? I hope so. 62 minus 62 rad 5s all over 1 squared minus rad 5 squared. It's 1 minus 5. It's negative 4. Where am I going here? Negative 4. Now, as far as canceling this, reducing this, I technically could reduce this weird little heart shape. If I was to reduce the 4 and the 62, I have to reduce both of those in this kind of weird greatest common factor distributy sort of way, where every term would be divided by the negative 4 if I do that. But anyways, yeah, that's the exact amount. And if I approximate that, it's 19.16. This was in meters, so this is in meters. Now, technically, yeah, I agree. You could have plugged this into the calculator, and that would have been fine. The only thing you would have had to be careful of is make sure you get these parentheses taken care of. So we've talked about multiplying and dividing. Turns out adding and subtracting radicals is tougher than multiplying and dividing them, which is perhaps counterintuitive. The same thing with fractions, though. Multiplying and dividing fractions is easier than adding and subtracting, right? Adding and subtracting, you ended up needing a common denominator. In a similar sense, we'll need to have like common radicals in order to combine like terms. And so if I'm adding or subtracting radicals, like radicals or like terms are going to have the same index and radicand, same tiny number outside the radical and the same insides. And so if I wanted to add these together, I've got 5 rad 7s minus 8 rad 7s. I just combine their quote-unquote coefficients. All right. Similar if I ask the question 5x minus 8x, they're still in terms of x's. And then plus rad 11 didn't have anybody that I could combine that with. And so that one's done. Now over here you might be like, aha, I can't combine those because those radicals are different from one another. Hey, Waddy boys, you guys got to be quiet, okay? Here we go. All right, so you might be like, well, Mr. Waddy, I can't combine those, and you're correct in their current form. But just like we used to have to get a common denominator in adding fractions, in this case, you are able to get a common radical, a like radical, because the square root of 20, remember our skills from the other day, I could break that up into a largest perfect square. Square root of 4 goes into that. And the square root of 4 is 2, and so I'd have 2 rad 5, and that is a like radical with 10 rad 5. And so I could combine those. That's a total of 12 rad 5s that I could combine. I'm not happy with my boxes there. Okay. Now for these ones. Now, like radicals have to have the same index and the same radicand, same little number and the same insides. So if I was, for instance, combining a square root of x, this is not like with those two because those are cubed roots. But those ones are both cubed roots. Their insides are x's, so I can combine them. So 6 plus 2 is 8, and they are still cubed roots of x. And so it's not that bad. You just got to be aware of like, oh, I could have, simplified some of these things. And then, all right, I'll do 24 real quick. Square root of 63 breaks down into 9 times 7. And so that's going to be negative 6 times 3 times rad 7, which is negative, negative 18 rad 7. And I'm going to combine that with the 4 rad 7. 4 minus 18 is a negative 14 rad 7s. And so sometimes you can simplify a radical in order to get like radicals. That's the idea. This one, it was this one and that one. Bam. All right, last question. Now, you can multiply in a distributive type sense, multiplication over addition, subtraction, all that. And so when multiplying these, I'm unsure. You know what? Square root of 5 times square root of 3 is square root of 15. And I know that that doesn't have a perfect square that goes into it. Minus, should I multiply this all out? I'm afraid of making big numbers. I could also have started by simplifying that if I wanted. All right, well, I'll multiply 75 times 5 is 375. And this is my reluctance that like, oh, wait a minute. That's a big number. Maybe I should have simplified it first. Like 25, for instance, would have gone into that. Now 375, if I divide that by 25, which is the largest perfect square that goes into it, it goes in, 15 times. There we go. And so I've got square root of 25 is 5, so minus 5 rad 15, and I've got a rad 15 here. Now, combining these, how many rad 15s is this piece? Well, there's an invisible 1 coefficient there, just like if I have x plus, or, well, I'll tell you what, if I did x minus 5x, remember there's an invisible 1 there, that would have combined to be negative 4x. Same idea here. So I've got 1 rad 15 minus 5 rad 15. It's going to be negative 4 rad 15s. And rad 15, we had already checked in our minds anyway to verify that that does not simplify any further. Okay. Are any of these that interesting? We'll be careful with this one. You cannot distribute an exponent over addition or subtraction. So 2 rad 5 minus 4 times 2 rad 5 minus 4. You could have used one of our patterns from back in the day. I just suspected that you guys might not have remembered those. Oh, let's distribute it. So when multiplying, the 2 times 2 I can do, and then the rad 5 times rad 5 is rad 25. This would be minus 8 rad 5s. Let me swap colors here for this. So this would be minus 8 rad 5s, and this one would be plus 16. So let's simplify and combine a little bit. 4 times 5. These I can combine. That's negative 16 rad 5s. I've got a plus 16 here. 4 times 5 is 20. And the 20 and the 16 can combine. Let's see that. That almost looked like a plus negative for a second. I don't know. All right, so 36 minus 16 rad 5. Now, one of the things that you got to be careful of when writing this is we still get in the habit of, like, rather than doing the radical in front of any other number, try to write it at the end. And then be careful, these cannot be combined because multiplication is taking place before the addition or subtraction. All right, I think that's all right. I think you guys will be good to go. All right, take care. Have a good day.